Hey, welcome back to the channel, everybody. This is Kevin, and in this week's video, we're going to take a look at yet another topic on Cisco's ENCOR exam. That's exam 350-401. And this is going to look a little bit different than previous videos because it's a replay of a webcast I did recently. Periodically, I'll go live on YouTube and we'll have what I call a net talk. We had a net talk covering GRE over IPsec configuration. We had a net talk covering DMVPNs. Well, this one is on IP SLA. SLA standing for Service Level Agreement. And with IP SLA, we can configure a router to send a probe out into the network, and we can have another router configured as a responder that will send us back statistical information about how the network treated that packet. We're also going to see an example of how we can make a routing decision based on delay that IP SLA can measure for us. And if you really enjoy this video, do me a favor, click the like button below, it helps the channel, and also please click on subscribe so you don't miss any of our weekly content. Now, let's dive into this net talk on IP SLA. Let's begin with a look at IP SLA theory. And again, SLA stands for Service Level Agreement. And a couple of primary things it's going to do for us. It can measure network performance. One of the reasons that I started using this back around the year 2000 was for quality of service. I was really into, I still kind of am into voice over IP. They call that collaboration these days. But I would set up a quality of service configuration in my voice network, and I had two ways to get from one office to another office. One way was over the WAN. I mean, that I'm not paying any toll charges to the phone company if I get to go over the WAN, but the WAN might get saturated. It might not give us really good conditions. We might be dropping packets. There might be excessive delay. So we could use IP SLA to send these probes out into the network to kind of test the waters, dip our toe in the waters and see if it's a safe environment. How beat up does our probe get? And when the receiving device got it, it would give us statistics like, here's how much jitter you experienced. Here's how many drop packets you experienced. So that's one application of IP SLA. Another one, and by the way, we're going to demonstrate both of these live today. Another one is to influence routing decisions. We have two paths to get from one router to another router. And the way we're going to do it later is we've got OSPF running as the dynamic routing protocol. And OSPF is all about cost. That's how it calculates its metric. It's going to say lowest cost wins. And the fastest link, the link with the highest bandwidth, that's going to be the lowest cost. That's what we're going to try to use. But if it gets saturated, if the delay is too great over that high bandwidth link, IP SLA can say, I know it's got a better metric, but it doesn't meet my criteria. So we're going to go an alternate way. I cannot wait to show you how that works. It is super, super cool. But going back to the voice option for just a moment, here's what I used to play with, and we'll set this up today as well. We're going to use a probe that looks like Real-Time Transport Protocol, or RTP. And that is what carries voice and video streaming media. And I can say that what we're trying to measure with IP SLA is jitter. Now let me define jitter for you because we're going to be working with that in a few moments. Jitter is the gap, typically measured in milliseconds, between the time that different voice packets arrive. I mean, here comes voice packet number one. Maybe behind that we have some sort of web packet, and it was delaying the next voice packet, and it comes in. Well, what was the duration between the time packet one was received, the first voice packet, and the time we received the second voice packet? Maybe it was 30 milliseconds. Well, we could set a threshold to say if the jitter gets too great, then let's route the call some other way. And we can also say how often do we want to send out these probes. We set a schedule, and I'll show you how to do that in a few moments. We could say, for example, we're going to be sending out packets every 5 minutes. I mean, we don't want to flood the network with all of our probes, and maybe it only makes sense to do that during business hours. So that's what IP SLA can do for us. I want to take you out and show you an example now. So let's go out to our demo gear, and I've got a fairly basic topology. By the way, if you're taking some notes on this, IP SLA has gone through a lot of name changes. I don't know of any technology where Cisco has changed the name of it so many times.
This feature that we're demonstrating used to be called the response time reporter, or RTR, the response time reporter. But there was an older version of that, which was also called RTR. It used to be called the real-time responder. And again, I first worked with that, and that's when it was called the RTR back in the early 2000s. Now it's called IPSLA, for Service Level Agreement. But they're all the same. You can use those terms interchangeably: response time reporter, real-time responder, IPSLA. And when we configure IPSLA today, we're still going to see some shadows. We're going to hear some echoes from the old response time reporter configuration. We still might have the occasional RTR command that we enter. Now, in our first example, if you take a look at this topology on your screen, we want to have router R1 send probes down to router R2. And those probes essentially are packets that put on a disguise. They do a little cosplay action, and they put on a disguise to look like different traffic types, such as voice packets. And when router R2 at the bottom receives those packets, it's going to send statistical information back to R1 saying, here's how this packet was treated over the network. Here's how much delay we experienced. Here's how much jitter we experienced. That's why we call R2 the IPSLA responder, because it's responding to the source of those probes with statistical information. And to begin our configuration, let's go over to router R2. That's going to be our responder. And we'll go into global configuration mode, and I'll say IPSLA and give some context-sensitive help, and you'll see that one of the options is responder, and that's what we want to do first. We want to enable the IPSLA responder, so we say IPSLA responder. And let's confirm that it is indeed active. Let's do a show IPSLA responder, and we can see that general IPSLA responder is enabled. That's what we're looking for. Now, by the way, an IPSLA configuration doesn't necessarily have to have a responder. I don't want you to think that it's always two parts. There's always somebody sending the probes and always somebody responding to the probes. It doesn't have to be that way in all cases. In fact, in our next demonstration, we're not going to have a responder. We're going to be sending ping packets out, and when we receive the ping responses back, we're just measuring a round-trip delay. So we're not even going to have a responder. So please keep that in mind. It doesn't necessarily have to have a responder. Now let's go over, and that was simple, wasn't it, on R2? We just gave one command, boom, we're done. Let's go back over to R1 now, and let's configure it to send those probes out into the network. And let's make those probes look like voice packets, shall we? And we'll go into global configuration mode again, and I'll say IPSLA, and you can give a locally significant instance number. We can have lots of IPSLA processes running at once. So I'm just going to say 1. I'm only going to have 1, but I'll say 1. And that takes me into IPSLA configuration mode. And if I do some context-sensitive help here, notice we can put on disguises for lots of different packet types. The one we're focused on is UDP jitter, because voice packets, RTP, it uses UDP, User Datagram Protocol, and we want to measure jitter. So I'm going to say UDP jitter, and then we can say, all right, where are we sending these probes to? And that's going to be the IP address of the responder. And if you look on the topology, you'll see that that is at an IP address of 203.0.113.1. Let's see, .2, excuse me. That wouldn't have worked. Yeah, it's a .2. It's that top interface on router R2. We're not done yet. When we send voice packets, in the Cisco world, they typically use a UDP port number in the range of 1634 through 32767. So it says, all right, what port number you want to use? And I'll say, I'll just use the first one that is often used for voice. It's going to be 16384. By the way, different vendors have different port numbers that are used for RTP, but that's what Cisco uses. And now, again, to continue making it look like a voice packet, we can say what sort of codec is it going to use. When we set up Cisco IP phones, we can configure what codec, what coder decoder they're going to be using. For example, if I were using either the first top two, G.711, those don't do compression. They give you a little better voice quality, but they take up more bandwidth. Payload only, they take up 64 kilobits per second of payload. And what you might see on a link that might be subject to being congested, we might see the G.729A codec. It only has 8,000 bits per second of payload. Of course, we have to have header, but the payload is 1/8 the size of G.711. So I'm going to choose that one. I'll say G729A, and we still get to be really specific about what this voice packet looks like. We can say, how big is the payload? What is my codec size in bytes, the number of bytes in the payload? Well, by default on a lot of Cisco gear, G.729 packets, they have 20 bytes of payload. Oh, by the way, they also by default have 40 bytes of header. Can you imagine that? The header's twice the size of the payload. That's a quality of service thing that we deal with in another discussion, but we can get around that. But we're done. We've been very specific, haven't we, about what our probes look like. They're UDP, just like voice. We're going to measure jitter, just like we need to know about voice. We're specifying our destination. We're specifying a voice port, a voice codec, and the codec size. Great. So we have now defined what our probes are going to look like. Now, let's set, in fact, if I give some context-sensitive help, one other thing I like to set is the TOS byte. The TOS byte, that's the type of service byte that we have in an IP header. And now a byte is 8 bits. And I'm just debating on how deep to go into this. If you've heard me teach quality of service before and get into quality of service markings, you're going to understand what I'm talking about. We typically use a marking called DSCP, Differentiated Services Code Point. In fact, pop quiz for anybody that knows, what DSCP value should we use to mark our voice packets? Chat it in if you would. There's a best practice recommendation. How should I mark my voice packets with DSCP? Go ahead and chat that in if you would. Not CS5. Voice payload packets. Yeah, Adam's got it. Excellent job, Adam. Adam says it's 46, which is called expedited forwarding. Yeah, we had a guest. Yeah, if you're signed in as a guest in chat roll, I'd really appreciate it if you put in your first name. That way I feel like we're having more of a one-on-one conversation if I could use your first name. But yeah, it's 46. This is a little bit weird, and it's a big binary discussion, and that's really not the point of today. But for those of you that are already familiar with DSCP markings, you know that it uses 6 bits to give us that 46. Well, if you stuck on 2 extra zeros to round out the full byte at the end of those 6 bits, where we had a total of 8 bits, and you calculated the decimal equivalent then, yeah, it's not going to be 46. It's going to be 184. And I need to specify TOS 184. So I'm giving this the same quality of service marking that a voice packet would have. Now that we've defined the probe that's going to be sent out, we need to set up a schedule to say, when are we going to send it? How often are we going to send out this probe? And let's say that we want to send, and I'm going to do it pretty aggressively because I want us in class to get some meaningful statistics. I don't want to have to wait for a couple of minutes to get one probe. So I want to set the frequency to every 5 seconds. Now let's say that we want to schedule those probes to be sent out starting now, and I want them to go forever. So here's how we create a schedule. Let me back out one configuration level, and I'll say IPSLA schedule, and I'll just give this a locally significant number. Schedule 1, and I'll say the start time is now. I want to start right now, and we'll say that the lifetime is forever until I shut this down manually and until I change the configuration. Then it's going to just keep running. And every 5 seconds, bam, 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 it's shooting out those packets that look a whole lot like voice packets. And we're done with our schedule. So we said, who are we pointing to? We set up how our probe is going to look and act. We said, how frequently are we going to be sending out those probes? And we said, go. We said, start right now. So what we're going to do right now is we're going to take our first Q&A break because I need to kill some time while those probes are being sent out every 5 seconds. So if anybody has, in fact, I'll go back on camera for this. I feel like we can talk better if I'm actually sort of seeing you face to face. But if you've got questions, I'm looking at both the YouTube chat and the chat roll. If you've got questions on the new Enterprise exam or the ENCOR exam, the new Enterprise exam track, or the ENCOR exam specifically, or something we've already talked about, go ahead and chat that in. Or if you just want to ask just whatever, if you've got questions, I've got opinions, and I can share those opinions with you. And sometimes the answer is, I have no idea, but I'll be happy to give it a shot. Let's see. Do you actually have any videos specifically for quality of service? Yeah, in fact, I've got a couple or 3 of them out on YouTube. In fact, one of my most popular YouTube video of all time is quality of service on Cisco Catalyst switches. So if you just search for Catalyst QoS Kevin Wallace, you'll find it. And I've got another video on YouTube, I think it's about half an hour long, that goes over the fundamentals of QoS. I think I might have another one that goes over the markings. So yeah, just check out my YouTube channel. My channel is K Wallace CCIE, by the way. K Wallace CCIE. What is the best CCNP ENCOR book to get? Well, the one that Cisco Press just recently came out with is the best that I've personally used. I haven't, full disclaimer, I haven't seen any other ENCOR books out there to compare it with. But I mean, it's a solid effort. It's a good book they came out with for sure. What exam do you recommend to renew the NP cert? This one, I would recommend ENCOR for that. Let's see. Do you have any security modules to prepare for ENCOR? Well, yeah, in the ENCOR video course, and that's what we're doing here today, we're celebrating the launch of our ENCOR Complete video course. We cover every single topic on the blueprint. I'll be showing you each of those topics. I'll be showing you all of our content videos. I'll just list them out. It's page after page after page. Yeah, we cover everything you need to know about security. Let's take a look at YouTube over here. Let's see. Will your new video course be available on O'Reilly? That's a great question. And the answer to that is no, it's not going to be available on O'Reilly. Previously, a lot of the courses I did went through Cisco Press as the distribution partner, and that's not happening with ENCOR. There's a lot of behind the scenes stuff that I won't get into, but it's good. It's all good, and I'm happy the way things worked out. But no, the bottom line is this is not going to be available on ENCOR. On Safari. So if you think I've got a Safari membership, I'll just watch it on there. It's not going to be available there. Why did Cisco decide to remove EIGRP from ENCOR? That's a great question. And here's my, again, total guess. I've not heard anything official from Cisco, but what that really reminds me of is when Cisco used to be a huge proponent of ISL, Interswitch Link, as their trunking protocol, even though there was this great industry standard called .1Q, Cisco really pushed theirs. I think it's kind of the same with EIGRP and OSPF. EIGRP was developed by Cisco. Even though they opened it up to the industry, not many people took them up on that. And OSPF by far, based on my surveys of my students, OSPF by far is the most popular routing protocol inside of organizations. Of course, BGP between organizations, but OSPF within organizations. I think they did just because OSPF is kind of leading the game right now. Now, not to denigrate EIGRP, when I worked at Disney, we had over 500 routers. All of them ran EIGRP. I love EIGRP. And just because it's not on ENCOR doesn't mean you're not going to need to know it for your NP, because it does show up in a big way in what's going to be, what I'm guessing for most of you will be your specialization exam. That's called a NARCE. And that exam is sort of like a troubleshooting course, but you have to know a lot about OSPF and a lot about EIGRP. It's just not in the ENCOR course. All right. We had tons of questions. We've got hundreds and hundreds of people joining us here today, so please don't take offense if I don't answer your specific questions. I'm doing my best to scroll both Q&A screens and try to pick out things that I think are relevant. But I think we've spent enough time now. Let me take my picture back off the screen. I think we've spent enough time now to get some meaningful statistics. So let's say show IP SLA statistics. And it says, scroll off the screen. It says the type of operation that we're doing is UDP jitter. And the latest round trip time, in other words, the time it took to get from R1 to R2 and back again, that was 2 milliseconds. We've also got the number of packets that we sent out. It looks like it was about 1,000 that we sent out, and we see minimum and maximum and average round trip times. But let's see, so here's the jitter. Yeah, here's what I was looking for. The jitter is averaging 3 milliseconds, and that is fantastic. Cisco says at maximum, you should not go over 100. Well, actually, the industry says you should not go over 150 milliseconds. We're at 3, so this is fantastic. And when you get in the voice world, they actually give a score to the quality of voice. For example, that codec, G.711, that did not do compression, it sounds better than G.729A that does do compression, but it doesn't sound much better. There's actually a way of scoring this, and it's called the MOS, the mean opinion score. The mean opinion score. And it is 4.06 in our case. And I'm telling you, for G.729A, that's really good. G.711 typically comes in at about 4.1. So personally, if just human speech, I wouldn't be able to tell the difference. We've got a network that is behaving very, very well. Probably because there's nobody on it. It's just set up. It is only set up for a lab environment. And that's the first IPSLA demo I wanted to share with you today. Our next demo that's coming up, and that's how we're going to be making routing decisions using IPSLA. And I'll go back to my topology. Actually, I've got a different topology, a little bit more complex topology. See here, take a look at the PC at the top, and it's trying to get down to the server. And it's going to go down to R1, and then we have a choice. We could go from R1 to BB2 for backbone 2, or we could go from R1 to BB1. Either path would get us to the server. But notice the bandwidth of those links. If I go down to BB2, that's a gig link. If I go down to BB1, that's only a 100 meg link. So, by the way, I'm running OSPF, which is only considering bandwidth. OSPF says you're going to go to BB2 because that's a lower cost. And yes, I did adjust the reference bandwidth, which is a whole OSPF discussion, to make this work. But let's just confirm that that's really what's happening right now. Let's go to our PC and let's do a trace route to the server. Let's do a trace route to 198.51.100.3. And notice the first hop obviously is R1. That's our default gateway. But the next hop ends in a .5. That's BB2. If it ended at a .1, that would be BB1. So that's no surprise. That's what we predicted OSPF would do. What we want to do now is we want to set up IPSLA to say, if the delay between R1 and BB2 is too great, then we want to fail over to this backup route. We want to start going to BB1. Yeah, the bandwidth is higher, but if it's saturated, that more bandwidth doesn't really help us. And what we're going to do to check that delay is we're going to configure IPSLA to do a ping test. We're going to ping from R1 to BB2, and we're going to measure that round trip delay time. The first step, if you're taking notes, the first step we do, and we're going to do all this on R1, of course, because that's where the packets are coming in from the PC. On R1, we're going to go into global configuration mode, and I'm going to create, for your notes, an IP SLA operation. I'll say IP SLA, and I'll just give it a number, locally significant number, and I'm now in IP SLA configuration mode. And before, remember, we used UDP jitter. I'm just going to do a ping. That's ICMP. That's an ICMP echo packet. Echo frame, I should say. No, that's right. It's a packet. It's an ICMP echo packet, a ping packet. And we're going to send a packet out, and it's going to be destined for gigabit 0/1 on BB2. And we're going to source it. We're going to source it from the incoming interface on R1. So we're coming in on gigabit 0/1. That's where we want to source this ping from. So let's set up the characteristics of our probe. I'll say ICMP-echo, and I'm going to say 203.0.113.5. That's that incoming interface on BB2. Who's my source IP address? Well, it's going to be that top interface on R1. It's going to be, let's see, it looks like 192.0.2.1. And that's all I'm going to say about the probe. It's just a basic ping packet coming from that top interface on R1 going to that top interface on BB2. Now, we set up the frequency like we did before. How often am I going to be sending out these probes? Let's say the frequency, again, I want some meaningful things to happen quickly, so I'm going to say the frequency is every 5 seconds. Now, here's where we get into that path selection logic. I'm going to say that if the delay is greater than the threshold, then I want to fall over to my backup route. That threshold is going to be measured in milliseconds. Now, right now, I don't want there to be an issue. Let's set it to 100 milliseconds. Surely, there's no traffic, there's no production traffic on this network. Surely the delay between R1 and BB2 is not going to exceed 100 milliseconds. If it did, we want to fail over to BB2. But we'll come back later and set it to something much lower. But this is more real world. I'll say that my threshold is 100 milliseconds. The next thing we do is we determine the schedule that this thing runs with. It's going to be every 5 seconds, but when are we going to start it? When are we going to end it? And we're going to do just like we did in the previous example. We're going to start it now, and we're going to run it forever. So I'll say IP SLA schedule 1. The lifetime is forever, and the start time is now. What we need to do now, this is where it gets a little bit trickier. Everything up to now has pretty much been identical to our previous example. But what we want to do now is associate this IP SLA operation. Here's a term for your notes. We want to separate it. I want to separate it with, or not separate, excuse me. I want to associate it with a tracking object. Now, a tracking object can keep an eye on something, and it can give us a state of up or down. Well, this tracking object is going to be measuring whether or not these ping response times are greater than the threshold or not. If we exceed that threshold, then this tracking object is going to be down. If we don't exceed the threshold, then the tracking object is going to be up. So let's create a tracking object. I'll say track, and I'll just give it a number. And what I'm tracking here is going to be based on my IP SLA 1 operation, which says I'm sending these ICMP echo packets, and my threshold is 100 milliseconds. And I'm going to say delay down 10, up 10. Let me explain what I'm doing here. The reason I'm saying delay is if I just briefly go over 100 milliseconds, I mean, I'm like 85 milliseconds, 92 milliseconds, and just for a split second, something happened and my delay got up to 105 milliseconds, but it dropped right back down. I don't think that's sufficient enough to reroute everything all of a sudden. I want to make sure that this is a condition that seems to be ongoing. So what I'm going to do is say, don't go to a down state unless this condition of exceeding the threshold has been going on for 10 seconds. And by the same token, if it gets better, if it drops below 100, it gets down to 98, but then it goes right back to 105, it was good just for a split second, that's not enough reason to come back into an up state. So I say up 10. I want to make sure that things are good for 10 seconds. Now, as I mentioned earlier, OSPF is influencing our routing selection. But remember, OSPF, in fact, you tell me, OSPF has an administrative distance of what? Who can be the first to tell me? What's the administrative distance or the believability of OSPF? What is the believability of OSPF? The AD. Anybody know? And by the way, there's like a 15-second between the time I ask something and the time you hear it. That's why I'm not immediately responding to your answers. Wow. Almost every person saying, you guys are doing awesome, guys and gals. Almost everybody's saying 110. Exactly. Okay. Well, how can I inject a route that's more believable than 110? I can use a static route. Check this out. I want to create a static route that says to get from R1 to this network at the bottom, that 198.51.100.0/24 network, the network that the server's on. I'm going to say to get to that network, I want to use a next hop address of BB2, just like OSPF told us to do. Under normal conditions, I want to use BB2 as my next hop. But I'm going to put a qualifier on that. I'm only going to say I only want to use that as my next hop if and only if my tracking object is in the up state. In other words, my round trip delay has not exceeded 100 milliseconds for at least 10 milliseconds. So let's do this. Let's set up a static route. I'm going to say IP route, and if I'm going to 198.51.100.0 with a 24-bit subnet mask, I want my next hop to be that incoming interface on BB2. I want it to be 203.0.113.5. I'm just double checking to make sure I typed things correctly. That looks good. I think I'm good there. And I'm going to say, here's the qualifier though. I only want you to do this if tracking object number 1 is up. Oh, I accidentally pressed a slash there. I only want to do that if tracking object number 1 is up. Okay, great. Now at this point, we're going to be using a static route because a static route has an administrative distance of a 1. That's a lot less. That's a lot more believable than OSPF. So we're going to be using that. And it's going to say, go to BB2 if tracking object 1 is up. What if tracking object number 1 is down? What do we do then? Well, right now it would just fail over to OSPF because that's the next most believable route. So I need to create another static route. And here's the key. Follow me on this. Here's the key. I need to make this other static route that's going to point to BB1. I need to make it less authoritative than the static route that goes to BB2, but I want to make it more authoritative than the route learned by OSPF. In other words, it's only going to kick in if that static route going to BB2 goes down because I've got too much delay. So I'm going to create a second static route and I'm going to give it a higher administrative distance. To do that, I'll say IP route 198.51.100.0, 24-bit subnet mask. I want your next hop to be 203.0.113.2. That's BB1. And here I'm going to give the number 2. Remember, a static route by default has an administrative distance of a 1. That's the one I just gave had an AD of a 1, so I didn't even specify it. Now I'm saying I want you to have an administrative distance of a 2. So it's only going to be used if that first static route goes away. Oh, I typed in the wrong address. Excuse me. What did I meant to type in a... what did I type in? IP route 203.0.113. .1. Oh yeah, I typed in, pardon me, I typed in .2. I meant to say .1. There we go. All right, just double checking. Yeah, that all looks good. Let's see what route we're using right now. Let's do a show IP route. And right now, to get to this 198.51.100.0/24 network, I'm going to this next hop. It ends in a .5. That's BB2. Okay, it looks like we're using BB2. That's because the tracking object is up. We can verify the tracking object is up by saying, show it to us, show track 1. And the state is up. And let's see, the latest delay was only 1 millisecond. I was going to set the delay to 1 millisecond to try to break it, but we might not be able to break it. We'll try though. But here's how we, one other command I wanted to show you real quick. Show Ip Sla Statistics. Show Ip Sla Statistics is another way to make sure that your SLA operation is running and is configured like you think it is. Now, what I want to do now is I want to adjust the threshold from 100 milliseconds all the way down to 1 millisecond in hopes, it might not, but in hopes that our tracking object is going to go down. Now, it's interesting that once I create this SLA operation and I start it, I'm not able to edit it. That is a heartbreaker right there. I have to actually get rid of it and then put it back. So I'll not give a lot of commentary here because we've already gone through these commands, but over the next minute, I'm going to be saying very little and typing very much. Let's get into it. I'm going to get rid of what I did before. I'll say no Ip Sla 1, and I'll say I want to create Ip Sla 1 all over again. I'll be using an ICMP echo message going to 203.0.113.5 with a source IP address of 192.0.2.1. Frequency is going to be every 5 seconds. My threshold is going to be 1. I'm going to set the schedule to have a lifetime of forever, and I want to start it now. Oh, okay. If we check the state of our tracking object now, we might see that it's down. Let's see. Let's see. Show track 1. Ah, it is down. Look at this. Yeah, it looks like we've been having some 2 millisecond round trip delays. So the state is down right now. Okay, let's do a show IP route based on that downed state. What is our next hop that we're using now? It's 203.0.113.1. It's BB1. How about that? In fact, let's double confirm that. Let's go back over to our PC. And let's do a trace route to the server, 198.51.100.3. Notice our next hop after the first router, it's a .1. It's going to BB1. And that is a look at Ip Sla. I guess until Cisco changes the name for a 4th time. But that's a look at Ip Sla.